So hi everyone. I've heard that there's a chemistry review session going on tonight, and so a lot of people are there and didn't show up to the Taylor series review session, and I feel like it's a fairly important thing, with regard to Physics 125, especially when you guys are starting to do pendulum problem and small angle approximation, and after that, um, a lot of other things that require Taylor approximation, uh, and this will not be properly covered in math or anything. And so I feel like it might be nice to do a little recording and cover whatever I cover tonight. Just like a brief overview of Taylor series and how it can be applied to solve physics problems. So just imagine that one day we're given a crazy function, like something like this. We don't really know anything about this, how this function behaves given our limited math knowledge. And so this is where Taylor expansion comes into play. The key concept behind Taylor expansion is very simple. We're trying to find a good enough approximation of a crazy function like this, and this approximation is very easy to manipulate, and namely, we're approximating things to be a polynomial, like something a constant times x plus a constant times x squared plus a constant times x cubed. So things like these are very easy to manipulate, to like do subtractions, multiplications, to like take derivatives, integrals. So it's sort of like the same concept or same philosophy behind what we did last week with Euler's formula. We transformed sine and cosine, some very hard to manipulate functions, into exponentials, where like we can do integrals and exponentials and multiplications very easily. So only that this week, Taylor expansion we're looking at sort of applies to a much broader spectrum of functions. So namely, like every single function we can Taylor expand it. There are definitely some limitations on what type of functions we can apply to expansion. Like it needs to be analytic at some point. It needs to be differentiable, but it's fairly safe to say that Taylor expansion applies to all functions, like with maybe a few exceptions. So let's go into the next slide and see how exactly it works. So just as I said, we are trying to find a good enough approximation of how this crazy function behaves at a given point, for example, at x equals to a. So we're not looking at the entire function because it's still approximation of the function is not going to tell us how it behaves at every point because we only need like only the function itself can tell us how it exactly behaves at any given point in its domain. But if we are a point of interest is only x equals to a or around that region, practically speaking, we don't need to care about how it behaves elsewhere. So we can come up with one approximation that's sort of good enough in that region. And one thing that I can come up with on the top of my head, I don't know if this is good enough, but it works at x equals to a. This approximation simply is fx equals to fa. So I'm just plugging in x equals to a into the original function and get a constant. And this constant function, f of a, or fa, I call this my crude approximation of this function fx at x equals to a. It's an approximation that is only accurate at this one point, x equals to a in space. And when I move to like a different point, x equals to a plus delta x, like it's a tiny distance away from this given point, my approximation fails. Um, so, but then it's a good starting point. Let's start from here. So we have fx equals to fa. What if we try to add in a bit more constraints on how our approximation should be behaving? So having only the function value at x equals to a to be the same between our approximation and the actual function is not enough. I'm not satisfied. So for example, we want to add in another constraint on how the first derivative of the function or the slope of the function of our approximation is. So we also want our approximation to simulate how this function change in function value at x equals to a. So it needs to have the same slope in addition to the same function value. So we're adding a second constraint, namely f prime x, or the first derivative of x, is f prime a. the first derivative of fx with a plug-in into x. So now basically we need to find a second term to add into our approximation, which is here right now. This is our current approximation. We need a second term so that we make first order derivative of fx to be the same as f prime a. And what kind of term should we add into this approximation? So we need to think about what kind of function has a non-zero constant as the first derivative. Basically, if we take the first derivative of what we have right now, we get 0 because it's a constant function. But we want it to be non-zero, and we want the slope to be exactly f prime a. So very naturally, we come up with this term. So f prime a itself is a constant, and that is exactly the first order derivative we want. And we add in, we multiply this with a second term, x minus a. This is to the first order of x, and we would take the first derivative of this term. Fx minus a, first order derivative, should be 1. So, and this term goes to 0 when we take the derivative. So, in this case, our modified approximation has the exact first order derivative value to be f prime a. What if we add in even more constraints? So we had a first order derivative. What if we want like the second derivative to be of our approximation to behave the same as the function behaves at x equals to a? So our third constraint will be f double prime x should be f double prime a. So with our original function, fx is fa plus f prime a times x minus a. We take the second derivative. The first term goes to 0. The second term, the first derivative is f prime a, which is a constant. We take the derivative again, and we get 0 again. So currently at this point, f double prime x is 0, and we want it to be f double prime a. How do we do that? In order to have a non-zero constant first, there's a typo here. In order to have a non-zero constant second derivative, we need to have a x squared term so that when we take the second derivative, it doesn't go away. So we also need to satisfy this boundary condition. And this term, 1/2 f double prime a times x minus a squared, seems to be the only one that works. When we take the first derivative, when we take the second derivative of this, we get just a constant f double prime a. X minus a squared times 1/2 goes to 1. And we can keep on doing this. We can keep on adding even more constraint regarding our third order derivative, fourth, fifth, and infinitely ordered derivatives. And then we're like getting even closer and closer to how the actual function behaves at x equals to a. So basically we can go on and on and on with the same process of adding even more terms to make our approximation even more fine-grained. You might have already noticed some pattern in our approximation. So the first term is fa, second term is f prime a times x minus a, and then it's 1/2 f double prime a x minus a squares. If we calculate the third term, it will be like fourth term, it will be 1 over 2 times 1 over 3 f triple prime x minus a cubed. It can go on, and if we use the sigma notation to to shorten this expression, we get something like this. So f of a, f prime of a, f double prime a, these are expressed with this term, f to the nth derivative a, so this is a constant, and it's n factorial in the bottom because it's 1 over 1, 1 over 2, and then after that we get 1 over 2 times 1 over 3, that's 1 over 6, so that's the n factorial term. And then we also get this x minus a to the nth power term that we observe here, x minus a squared. The next term will be x minus a cubed. So this is how we derive Taylor expansion, the general form of Taylor polynomial. So why are we talking about Taylor series? Why is this useful, and how does it relate to Physics 125? Practically speaking, I mean, obviously we can use it to estimate values, function values, and taking a step further, we can approximate the behavior of a function, namely like the slope or the second derivative or whatever's derivative regarding a particular reference point. namely the point we are approximating the function around. We can also use it to prove theorems regarding particular functions, and like do small angle approximation, do small distance approximation. We'll see examples of these coming up. There are some frequently used Taylor series that I recommend memorizing. So these will be, I'm pretty sure that out of all the Taylor series Taylor expansions they're going to use in Physics 125 first and second quarter, these 5 covers like 99% of them. So out of these 5, there are like 3 that are especially important that I definitely recommend memorizing. The first one is the exponential e to the x, approximating to 1 plus x squared over 2. You only need to memorize the first 3 terms. Usually you'll only be using the first 2 terms. Sometimes you'll be asked to do like a quadratic or the second order Taylor approximation. In that case, you'll be using the 3rd term. Another thing is sine x. You'll be using it at like very soon with a pendulum problem. Sine x approximating to x minus x cubed over 3. Usually you only need the first term. Sine x is x, or sine theta is theta. Another thing is this 1 plus x to the alpha's power. Alpha is constant. Approximates to be 1 plus alpha x. So that's another thing you need to memorize. Very, very frequent, very, very common in Physics 125. Let's see how it applies to something that we've already encountered. Last week, we did a very hand-wavy proof of Euler's formula or Euler's identity. We talked about like unit square and all that, but to get a more mathematically rigorous proof, we can just apply Taylor expansion. So as we might have noticed, on both sides of our Euler's formula, e to the ix, and on the right side, cosine and sine, all of them are like Taylor expandable. Like they were, all 3 of them were on the list I showed you guys in the previous slide. So I'm not gonna go into the calculation here, but basically the concept is e to the ix. We just take it as a constant and do Taylor expansion. We get something like this. And on the right side, we have cosine and sine. We can Taylor expand each one of them and sum them. And we sort of see that they give you the same polynomial. And for any given function, however crazy it is, there's only one well-defined way to express it as a polynomial. Because every single term in the polynomial are orthogonal to each other. Things like x cubed, you cannot get x cubed from summing x squared or x. So these are orthogonal to each other. And so there's a well-defined way to express e to the ix in terms of polynomials. There's also a well-defined way to express cosine and sine in terms of polynomials. And when you really expand them, it should be fairly obvious that they're the same. So that's how we prove Euler's identity using expand. And some even more practical applications. We have the pendulum problem. So in the pendulum problem, we are studying the motion of a pendulum when the angle between the string and the vertical line theta is considered to be small. So we can set up an equation equating the force, the centripetal force, the force along the line and along the string, and force and the component of gravity that's going in that direction. So we're seeing this equation F equals to ma, which is ml theta. So this notation means like second derivative of theta, the acceleration, the angular acceleration. So this is basically telling you about the tension force, the centripetal force on the string that's applied on the mass. It should be in opposite direction, but in the same magnitude of mg, which is gravity, in that direction, sine theta. So we set up this equation, and then we get a differential equation, theta double prime plus g over L sine theta is 0. This is not that obvious what the solution is, but if we apply small angle approximation, the Taylor expansion of sine theta, the first term is theta. So we just replace sine theta with theta, and we get a good enough approximation of how the pendulum behaves when theta is small. And then we get this. Theta double prime plus g over L, which is a constant, times theta equals to 0. And if you recall from last week when we talked about Euler's, when we talk about sinh and cos, sine and cosine solving differential equations, um, sine and cosine, those are the solutions to this differential equation, and uh, the exhaustive solution to this equation will be a linear combination of the two. And in second quarter physics, maybe between the first few lectures of second quarter, you'll be dealing with something called electric dipole, which is basically two charges, a positive charge or a negative charge, or two positive charges that are very close to each other, but still not on top of each other. And you'll be asked to explore how the electric field or magnetic field behaves like far away from these two charges. In that case, you'll be using small distance approximation. So you'll be calculating the electric field as if the distance between the charges are not small. And then after that, when you get the equation, you apply small distance approximation, and then you get how electric dipole behaves. So that's basically all I have for tonight. There's actually 3 handouts on my website. Um, there's some very useful practice problems on the Taylor series handout. Um, so it might be useful or helpful to like try those out and see um, how you can apply Taylor expansions to some of the physics practice problems. And actually, some of the problems on that handout are selected from previous physics midterms and finals. So those are very useful. And there are also 2 other handouts, one titled Benjamin Moy on Taylor series. Ben Moy, he was a fantastic ISP tutor who just graduated last year. So actually, my session tonight was mostly like based on his handout, and he has some like very detailed explanations of how Taylor series are derived and how it can be used to solve like problems like the pendulum problem, dipole problem, and other physics problems. So that might also be helpful. And I have a nice, interesting PDF called Karl Marx on Taylor series. So it's just like Karl Marx doing math. Um, it's not as useful as the other two, but might be entertaining to look at. Yeah, that's all I have tonight. Thanks for watching.